Hello, everyone, and welcome back. In this series, we are attempting to write an operating system from scratch. And today we will be starting on the bootloader. So, for the bootloader, I have started here creating a new file called bootloader.asm. We will have a single file for this bootloader. It will do very few things, just the essentials to get us set up for loading the second bootloader stage, which will be a bit more involved. Right, so I've also gone ahead and set up a bit of a make file here. So what it does is basically calls phasm and copies the result bootloader binary into the output directory, which is the build there. I've also went ahead and created a global make file for the project, and I primed it with the bootloader stuff. So it just goes into the bootloader folder and calls make all there. I have also, and this is the final thing I promise, I've created this box RC config file, which will basically use to test that our bootloader is doing what we expect it to do. And we will be using Box for this, for the start of this series, because it's easier to debug, I find, real mode code in Box than it is on QEMU or other virtual machines. So what we're doing here is that we're just loading the binary we've built as a floppy. And the reason why we're loading it as a floppy and not as a hard drive, as you can see commented out here, is that we still haven't tackled anything that has to do with partitioning that is needed for a hard drive to be read correctly. So the floppy format does not really need any partitioning. It just relies on sectors. So that's why we can just load our file, our flat binary file into it and have it execute as is. Right, so let's get into it. So we are in real mode, so we will make sure to set ourselves in real mode with the U16 directive, which will ensure that our file is assembled in 16-bit instructions. Okay, so what we'll do now is we'll just try to do something basic, okay? Let's just try to print hello, okay? So before we do that, let's go and find the tools we will need. So let me just go back to the browser here. Right, so the things we will need to print stuff is interrupt 10. Open it up here. So interrupt 10 is video bias services. Basically, we have here functions that we can call to do something, either draw pixels or write text. The one that will interest us for now is this one, is int10 with argument e, which is write text into the type mode. Okay, so this interrupt here takes argument e in AH, and in AL the ASCII character that we want to write. BH is page number. We don't have to worry about this. We'll be using page number 0 for everything. And BL will be the foreground pixel color. And I have here a list of colors. There are 16 of them, since we are in 16-bit mode. Actually, no, in 8-bit color modes, the BIOS says. Right, so, and the, so basically we have 8 bits, and the high 4 bits represent the background color, and the low bits represent the foreground color. So we will basically have just 4 bits to play with for the foreground color, since we will not be changing the default black background color. So we have here a few choices we can use. White is the default for foreground color, and black is default for background color. So we'll see. Okay, so this one here is what we can use to print something to the screen. So let's just follow the recipe and see where that gets us. Okay, so right. First of all, let's do something like this, and we will just jump to forever. Okay. So this will be just needed so that we don't go out. So we'll loop forever here so that we can see what we printed. Right. So let's set up the recipe for the interrupt 10E. First of all, we'll need AH to be 0E. So move AH 0E H, right? We will need BX. BX is basically BL plus BH. We move BX. So what we want is, let's choose a color. Let's say cyan. Cyan is decimal 3 and hex 3. So yeah, okay. So BX will set to 0, 3, which will be background black 0, top 4 bytes, and yep, there we go. So background is black and foreground is cyan. Right. Then we will. What else do we need? What does the recipe say? We'll need the. Oh yeah, of course. Move AL. So AL will need to have the actual character we're printing. So H, for example, and then we'll call the interrupt. Just call it this way, 010H. Okay, I think that's about it. If we're not forgetting anything, no, I think it should be fine. All right. Okay. So let's try to assemble this and see what it gives. Okay. So I'll just go. Actually, I need to go here and make all. Of course, I also need to force it. Cool. Okay. Right. Cool. So we have assembled our file. As we can see here, it was assembled and it had 11 bytes. So what we can do now is we can actually see the content of our file. Okay, so we can deassemble it. The way to do that, if I remember correctly, we'll use objdump, and I guess it's what is it? Intel. And here we'll have I-8086, and we'll tell it to deassemble it. Oh yeah, of course. We'll tell it also that it's a binary target, and of course we need to give it the build. There we go. Cool. Right. So also, just to to have this work as we want it to and have the actual correct addresses, we'll do a bit of this VMA, or actually, yep, adjust VMA, and we'll set it to where it will actually be loaded, which is 0x7C00. Right, cool. So so we move E into AH, we move 3 into BX, and we move 68, which is lowercase h, into AL, and we call our interrupt, and then we jump into the same address, which is our forever loop. Cool. It's working as intended then. Right. So let's call box. Right. I need actually to bring this up here. Hopefully it will be. Oops. Right. Okay, cool. Okay. No bootable device. That's weird. And why is that? Why is that? Actually, no bootable device. So the file should have been there. It found the, oh, actually I know why. Right, okay. So our disk needs to be at least 1 sector large, our floppy disk. So what we will need to do is we will need to pad it until it's 1 sector large. So the way we do that is we'll just let's call it pad. We'll just add a few 0 bytes. Actually, it should be a byte. It will be 0 and no, actually, okay. The way it works is we need to tell the number and then the 0. Okay, so the number is, we'll take the current location, which is $, and we'll subtract from it the start of the file, and these go like this. So this would basically give us the size of everything that came here before us. And what we want to do is we want to take a single sector and just basically calculate how many zeros, how many padding bytes we need to add to this file so that it can be 1 sector large. And a sector, of course, is 512 bytes. And of course, we'll just duplicate 0 this number of times. All right, let's save this. Let's rebuild this. Oops. Yep. There we go. Cool. And here we can see that our file, the binary file that we built, is actually now 512 bytes wide or big. And what we will do is we will also try to dump it. And yep, you can see that we have the same instructions, but here after the jump, we have a bunch of zeros, which overjump just basically collapses into this kind of stuff. Let's try again then. So box, just bring this screen here. Okay. Oh, okay. Yeah, we actually forgot something. For a drive to be bootable, as we've said before, it needs to have a set of bootable flags, a flag that basically sets it as bootable, and we can do that by adding 2 bytes, 55 and AA. Of course, here we need to add the 0, and of course, since we added 2 bytes, we need to subtract them here, so that we can still have 512 bytes total. Okay, let's give this a name, since we've started giving stuff name. Let's call this boot sig for boot signature. Let's just align these two. All right, cool. Let's remake this then, and we'll see. All right, so it's still 512, and if we dump it again, oops, sorry. If we dump it again, we can see that we have a bunch of zeros, and then at the end we have 55 AA, which is our boot signature. Right, let's try to side this time. All right. Okay, cool. So we have, I don't know if I can zoom in a bit more here, but it should be fine. So here we have the H that we've printed, written just after the BIOS messages. Okay, cool. So what we can do now is we can just add a bunch more letters, right? So let's add a few of those and try to write hello. Right, so let's compile this again and run it. And we should have hello. Cool. The only issue is that this way of doing things is not really that great, because imagine you want to write a sentence. How do you go about that? Right, so what we need to do is actually to create a sort of function that will take in a sentence and print it for us, character by character, using this interrupt here. And the way we can do that actually is we can go here, define some sort of sentence. Let's call it hello. And this will be, actually, just hold on, just, there we go. So this will be hello boot world, something like this. And we, of course, we need to terminate it by a 0, C style, so that we know that we've finished printing everything that needs to be printed. And now what we'll do is we will try to print this sentence character by character. And to do that, we'll need to learn about a few other assembly instructions. And the first one we need to learn about is this one here. Hold on. Yep, this one here. Load string. The one that interests us is load string byte, since we are working in ASCII, so we only have single byte characters. And the way it works is, let's ignore the description for now. Let's just go straight to it. So the way it works is, if we have a flag, the direction flag is set to 0, then we will load the from the source into AL, okay? And then we will increment SI, okay? So basically, if you have a source, we will load from the source into AL, and if the direction flag is 0, we will increment SI. If it's not 0, if it's something else, if it's 1, we will decrement SI. Okay, so it's straightforward enough. And the way, as I said, what we're interested in is load string byte. And the way this one works is that the source for it, you can see that it doesn't take an argument, unlike load s, which takes an argument for the source. This one here just assumes that the source will be si. So what it does is it will load the current character that's pointed to by si into al, and then if the direction flag is 0, it will increment si, which basically means we will point to this next character. All right, so let's do that. So we'll create a function called printfunc, and first thing I'll do is, so what we need to do, actually, let's just define a bit of a usage contract, okay? So the way this function will be used will be move si some string address, right? And then call printfunc. So that's how we will land in printfunc. So we know that by this contract here, si would have already the string address. So we just need to go ahead and call load string byte, which will basically, if we add a bit of a comment here, so loads, let's imagine that the string is an array and si is the index into the array. So it loads the character that's indexed by si into al, which is basically where we wanted, where the or rather the int 10h interrupt wants the character to be. Right, so what we need to do now is we need to, we need to check if the character is not 0. Basically, if al is 0. If it is, then we need to basically get out. So we'll use this conditional jump, which is jump if 0. And we'll need to jump somewhere. And for now, that somewhere will be, let's just call printfunc. Actually, if I can type printfunc and, okay, as a label. And let's just jump there. Okay. And since this function is called with call, we need to return the execution flow to our caller using the ret keyword. Right. So if we know that jump that al is not 0, so basically al is something that we want to print. It's part of our string. So we will basically just set up the call to the interrupt. So the way we do that is we'll just move ah the byte. So what was it? 0e. Yep, it's 0e. And then we will move into bx the word tree, which is the color that we want, and then we'll just call the interrupt. And this by here, so okay, hold on, let me just add a few. So set up the tanh e call interrupt, let's call it that. This is the part of the setup, and this one is call the interrupt. Right, so now we've printed one character, so we need to print the second one. We already know, okay, here is then since df is 0, since we didn't set it to anything else, it needs to be 0. Then si will be incremented. right? So we don't need to worry about SI now. We just need to basically jump into print func again. And the way it works is that we load character H. It's not 0. We don't take this branch. We go here, we load 0e into AH. And the reason why we do this is that sometimes interrupts do override our registers. So we need to make sure that we know what's in them. Right, so we move 0e into AH. We set the color that we want, foreground 3 and background 0. We call the interrupt to print the character, and then we'll jump back to load string byte. And since SI was incremented, that means that we're pointing to the E now, and then we go again and again until we reach the exclamation point, and then we print it. We jump back. SI will point to this character here, which is 0, and then we will take this branch, jump 0 branch, will come up here and return into the color. All right, cool. So let's set up a call to our function. Move SI hello. That's why I called. Yep, got it. Great. And then we call print func. So if everything goes well, let's make clear and okay. It's not happy now, is it? It's not printing our hello boot world. Okay, let's try to see why that is. Okay, so instead of calling box, we will call box debug, and that will basically let us set breakpoints. So what we can do here is set B 0x7c00, and we can use blist. See that, yep, we have our breakpoint here, so that 0c00, and then C to continue execution. And here you can see that the program continued the execution, and we've stopped right when we landed on our first instruction. So this is move SI 0x0017, which is this hello here. And I see what the issue is. So see this here, 0017? It points into the 17th byte of memory, which is something that we haven't touched, because our string is actually set after our code here. And our code starts at 7c00, which means that our string would be something after 7c00. And what happened here is, actually, hold on, let me just quit this. So what happens here is that when you use addresses, like stuff like this, in your assembler, the assembler will basically consider that the address is relative to the start of your assembly file. Okay, so here, this is our first instruction. So before it is our 0th byte. And if we count the bytes of every instruction we've written here, we can find that hello here, the H, will be at the 17th byte, starting from move. Except that when the file gets assembled, that's the value that gets written here. It gets hard-coded into here, right? So hello would be replaced by 0x17, and then it gets moved into SI. But when we get executed, when our code is executing, it's not at 0000. It's at 7c00. So what we need to do is we need to tell the assembler that our code will actually be moved to somewhere else, and that any computation that it does on the relative addresses would need to take into account that we are moving somewhere else. And the way we do that is to actually use the org directive, and we tell it where we are expected to be. And if I save this and rebuild and redump this, you can see here that, yep, see how it took it into account now. Move SI now is 7C17. Yep, 7C17 instead of just 017, the way it was before. And if we get down here to 7C17, you can see that this is our string. So H E L L O comma space, etc. Right, so let's rerun. We don't need to debug it anymore, so let's just rerun box. And there we go. We now can print strings however we want. We can try some other strings if we want. We can go ahead and right, so let's go ahead and do this and recall print. Actually, let me just quit. Whoopsie. Let's just quit this so that you can see the code. Right, so print func. Added this new string, and what we need to do actually is have a CR string, which will be which we'll use to as a carriage return, and this would be 13H, if I remember correctly, is carriage return. We'll see. Right, so let's go ahead and remake this and run it. Yeah, so we need to call the carriage return, but it's still printing our code, so it's cool. Let's also print the carriage return cr call print func. Let's see if this works as we expect. Great!
A great success!
Right, let's have a bit more fun, right? Let's call this start and have a jump start. Okay. We don't need this anymore. We don't need this anymore. Right, let's do something like this. Actually, maybe you'd want to see the code. Right, so what I did is I created a label start and put into it the hello print and the carriage return, and then we jump back into start. So basically what we're doing is we're printing the hello forever. Let's print hello forever then. Right, so it's built. Let's run this. And here we go. It's great. You can see that it's a bit junky, it's a bit slow, but what do you expect? It's the it's the Bootloader graphics. They're not supposed to be very quick. Right, cool. So, well, that's it for this episode, and on the next one we'll tackle the actual big challenge, which is loading something from disk. See ya.